Measuring kinetics in practice can be really tough. We are dealing with events that are happening on incredibly fast timescales potentially. And one of the techniques that people turn to in labs to actually figure out what are the kinetic parameters involved in protein association with some ligand is a technique referred to as surface plasmon resonance. And what SPR is it essentially relies on a concept that many of us are already know about from waves and optics class, in which if we have some kind of prism in which light can pass through it, and the light will be bent accordingly depending on that prism's or the medium's index of refraction. If we draw a normal like this, and we analyze how an incident light ray changes as it passes through the prism, we will note how there is some particular angle to the normal, theta c, the critical angle at which we realize total internal reflection. And so typically what we see in physics is a graph that looks like this, where this axis will be theta, and this axis will be reflection, and this will be 1.0, so 100% reflection, and we'll see a line that a function that resembles this, and then once we reach our theta c value, all of our light or any light ray that enters our prism with a theta greater than or equal to theta c will have total internal reflection. Now, what makes things interesting in surface plasmon resonance is if we coat the prism with some kind of metal, and it's commonly gold, but we'll just call it a metal surface for now. What happens is on the metal surface we have electrons present. The electrons will completely cover the surface, and the electrons will interact with the light ray. And so the classical model that we see here, ignoring the electrons, will begin to deviate from what we see. And so what happens next is there will be some theta at which there's some absorbance occurring. And what happens at this theta, I'll call it theta naught, is a light ray that comes in and interfaces with the metal surface will generate something referred to as a plasmon wave. And these plasmon waves result in us seeing this theta naught value. And so with this theta naught value, what scientists do in lab is they will now tack on something referred to as a dextran matrix. And on this dextran matrix, we'll attach some ligands. And ideally these would all look exactly the same, but you guys get the point. And each one of these blocks I will call B. And so the goal here is to determine the kinetic parameters of A binding to B, where A can be some kind of protein and B would be some kind of analyte that biotech is interested in determining for some drug candidate. And we want to know how readily, or we want to know the kinetics behind which A and B will associate, little ka, and how readily they will dissociate, little kd. And so what we do in the labs is we will expose the dextran matrix with the ligand attached to various concentrations of our analyte A. And so we'll have A floating around in solution at varying concentrations. And so what will happen over time is A will have some affinity for these ligands and will bind to it at a certain rate. And as we are recording how theta naught is evolving over time, theta naught as a function of time, we will be able to have some kind of understanding as to the kinetics that are involved in this association or dissociation. And so what we get out of it are plots that will have a y-axis that typically will have some kind of arbitrary units, but it will refer to an absorbance value. So I'll just call this absorbance, and it's arbitrary units. And then this axis here will be time. And so at some given concentration Ca, we will note how as A binds to B, the ligands, the absorbance value is increasing. It's altering the electrons' interactions on the metal surface with the incident light rays, which is resulting in greater absorbance. And then we will realize some area in which we see linear behavior, and this is when we've reached equilibrium, which is pretty boring. And then we will enter a third regime in which we see dissociation. And so from the initial regime here, we can evaluate with some math equations what Ka would be. From the linear regime here, we would realize or be able to calculate what Keq is. And then from this third regime, we can calculate what our kinetic parameter little kd is. And so with these values, we can now come to a conclusion that we'll have a much better understanding of how a protein is binding or interacting with an analyte much better than just knowing what the equilibrium value is, because quite often in practice we're very interested in the kinetics and not just the equilibrium values. And so it is very important to understand how these processes work and how we actually evaluate these things in practice. So I hope this clears things up for people who are new to surface plasma and resonance. And let me know if you have any questions. Thanks for watching.